and welcome to this webinar, Reverse Engineering and Analysis of Polymer Materials and Coatings by GC/MS Pyrolysis. This event, brought to you by Paint and Coatings Industry Magazine, is sponsored by Quantum Analytics. I'm your moderator, Kristen Johansson, Editor-in-Chief of PCI. Thanks for joining us. Today's presenters are Rogine Belganet and Dr. Rigoberto Advincula. Rogine is the Technical Director at Frontier Lab Americas. As a former user for more than 5 years, Rogine joined Frontier Laboratories in 2017. She graduated from the University of Houston with a Bachelor of Science in Chemistry. She also holds an MBA degree concentrating in strategic marketing from the University of Houston, Victoria. As an analytical chemist, she worked with various analytical instruments such as Pyrolysis GC, TGA, FTIR, and X-rays for material characterization, polymer identification, and contamination analysis. Rigoberto Advincula is a professor at Case Western Reserve University in Cleveland, Ohio. He is a fellow of the American Chemical Society, a member of NACE, SPE, ERG, MRS, and AAAS, and a frequently sought-out speaker and expert in polymer materials, coatings, and sensors. He recently has been appointed to the World Economic Forum Advanced Materials Council. His group does research in polymer materials, nanocomposites, colloidal science, hybrid materials, and ultra-thin films towards applications from display coatings to biomedical devices. He is also pioneering a number of 3D printing routes towards new polymer and nanocomposite materials properties. He consults for a number of companies focusing on the most challenging problems and definition of structure-property relationships towards commercial applications. Don't forget to submit your questions, and later in the program, we will address as many of them as possible. Today's event is being recorded and archived at pcimag.com. And now I'm excited to turn it over to Rogine.
All right. Thank you very much, Kristen, for the introduction. So first, before we actually start the content of today's event, we would like to ask you a quick question for us to understand our audience regarding the reverse engineering. So if you could please take a few seconds to answer the question of, are you currently performing any reverse engineering in your laboratories? Either you are already doing it, or we aren't now, but actively planning on it, not right now, but maybe in the future, or no current plans. So for a few seconds, if you could please answer this question. All right, that's great. So it seems like a majority of us today are currently doing reverse engineering. So hopefully by end of today's event, you'll have a good understanding of how Pyrolysis GC/MS can do reverse engineering, as well as deformulation or reverse engineering for failure analysis. Or if you're currently using Pyrolysis GC/MS, hopefully you'll learn more about this technique. All right, so let's go ahead and start our event today. Before I start on a technical slide, I thought to just give a brief summary about who we are. Frontier Labs was founded in 1991 by Dr. Chu Watanabe. Chu-san, with the support of some of the polymer scientists at Nagoya University in Japan, developed a pyrolyzer based on a vertical microfurnace design. We are a global corporation, and our main products are a series of pyrolyzers, such as the multi-shot and a single-shot pyrolyzer. We also have a rapid screening reactor for catalyst analysis. Those are the tandem and the single microreactors, as well as a line of ultra-alloy stainless-steel capillary columns. So here is our agenda for today. In the first part, we will discuss the microfurnace Pyrolysis GC/MS system configuration, its modes of operation, and how you could use it to perform quality control, deformulation, contamination analysis, unknown identification, and even failure analysis, while increasing your laboratory efficiency by eliminating sample pretreatment and the traditional solvent-based technique. So by the end of part 1, we will have a good understanding of how microfurnace Pyrolysis GC/MS system uses its multiple modes of operation for chemical composition analysis. And then the second part will be applying part 1 to polymer application presented by Professor Advincula. With Pyrolysis GC-MS, you really can analyze any form of sample, such as solids, liquid, and gases by GC. Sample preparation is really easy and straightforward. You just place micrograms of your sample inside an inert sample cup and then perform the analysis. So a solid sample can be analyzed as is. You don't need to have any solvent or perform any solvent extraction. And then also, depending on your sample type, you can use an appropriate sampling tool, such as the micropuncture, to place your sample inside the inner sample cup and then start your analysis. Here is the system configuration for Pyrolysis GC-MS. So the microfurnace Pyrolysis GC-MS uses a microfurnace pyrolyzer as a programmable temperature inlet to a gas chromatography mass spectrometer GC-MS system, as you can see here. The microfurnace is actually directly connected to your GC injection port. There won't be any transfer line, no active site, and also no cross-contamination. Here in this slide, you can also see some of the accessories, such as the microjet cryo trap that uses liquid nitrogen to trap and focus all those light and volatile compounds at the head of your GC column. Selective sampler is another accessory that is used for hard cutting mode of operation that I will discuss shortly. Also here shown are the auto shot sampler that is on top of your microfurnace for automating the analysis up to 48 samples, and also the vent-free GC-MS adapter that allows switching the columns without venting the MS. Also on the left-hand side, you can see the F-Search interpretation libraries and the pyrolysis data book that are used for identification of polymers and additives. So with microfurnace technology, sample introduction is nearly instantaneous. The sample is placed in an inert sample cup and is held at near ambient temperature in helium while is not subjected to any heat before the analysis starts. The microfurnace is then preheated to the desired temperature that is precisely measured with a thermocouple sensor. The sample cup then drops into the quartz pyrolysis tube where the sample is rapidly and reproducibly pyrolyzed. The pyrolysates are then directly swept onto the GC column for separation and detection by your MS. So this technology really and directly deposits all the pyrolysates on column in a single step for a continuous pyrolysis mode. This single-step process allows low and high molecular weight as well as polar compounds to be detected and analyzed. Microfurnace also allows a full-range evolved gas analysis, EGA, to obtain a thermal profile of an unknown sample for any light compounds, additives, volatiles, oligomers, polar, heavy, and polymeric compounds. These EGAs, evolved gas analysis experiments, can be performed from 4D C to more than 1000 C and correlate results to the well-established TGA, thermal gravimetric analysis techniques, throughout the entire temperature range of the experiment. The microfurnace technology also guarantees reproducibility and accuracy of the temperature within plus or minus 0.1 degrees Celsius. All the surfaces are quartz or temperature stable deactivated. So the multi-functionality, purpose and capability of the microfurnace pyrolyzer allows you to perform 4 main analytical techniques. You can simplify pyrograms and chromatograms by combining these techniques in accordance with purpose of your analysis. So your data analysis become easier, more targeted, rapid, and effective. So you could perform evolved gas analysis, EGA, which is a thermal analysis of a sample. From the obtained EGA thermogram, you can understand the behavior of the sample toward the temperature by temperature program heating of the sample and directly detecting the evolved gases with MS. You could also perform single shot, which is flash pyrolysis and is an instantaneous pyrolysis of a sample. On 1 pyrogram, you observe polymeric pyrolysate, any volatile compounds, and their decomposition products. And also the third mode of operation is a double shot analysis that operates both the thermal desorption and the instantaneous pyrolysis. You obtain the separation analysis chromatogram of volatile compounds and the pyrogram of instantaneous pyrolysis in one set. And then the last mode of operation you could perform is the hard cutting EGA GCMS, which is based on the information from your EGA data, in which you really selectively operate the thermal desorption or temperature program pyrolysis in each temperature fraction where the gas evolves and individually obtain separate analysis. So as we just learned, you can actually perform multiple analytical techniques in addition to flash pyrolysis using your microfurnace GCMS system. Now, to chemically characterize an unknown sample, we have developed a series of techniques referred to as the method map. This chemical method map really provides you with 2 simple steps to determining the organic composition of any unknown sample. EGA, evolved gas analysis, is your first step, which provides you with a clear picture about the thermal profile of your sample. The second step is then to use your EGA thermogram to define the thermal zones of interest. So really, EGA guides you on what to do next. It will show if a thermal desorption, hard cutting, or flash pyrolysis is needed, or maybe even if a combination of these techniques is required. So now let's look at each modes of operation in a little bit more detail. What is EGA? Gases evolved during program heating of sample are directly transferred into MS to monitor thermal profile of the sample complexity. How does it work? The sample is dropped into the furnace, which is at a relatively low temperature. The furnace temperature is then programmed to a much higher temperature. A plot of detector response versus furnace temperature is then obtained, as you could see on the right-hand side. Also, it's important for me to mention that to perform EGA, a short and deactivated tube is used, no separation column, because again, that's a thermal analysis of your sample. Here you can see an example of an EGA thermogram. We perform EGA on a cosmetic eyeliner by setting the furnace temperature from 40 to 600 C. As shown here, 5 peaks or zones are detected that we are calling it or naming it A, B, C, and D. And this info really guides us to the next step to perform separation analysis. And what are the advantages of EGA? Reflecting thermal property of the entire sample, similar to your TGA-MS, rapid screening of samples, and also obtaining optimal thermal desorption and pyrolysis temperature. Now that you perform your EGA, you want to perform any of the separation analysis, you could switch your EGA tube to the separation column using your vent-free adapter. So what is single shot? Single shot is a term used to describe the pyrolysis of a sample at a fixed temperature. It's the same as the flash pyrolysis. How does it work? The sample is instantaneously subjected to a temperature high enough to break organic bonds. The degradation products or pyrolysate provide insight into the chemistry of the initial sample. So using the EGA of the eyeliner from the previous slide, we identified the optimal temperature for the single shot at 550 C. So 550 C is the optimal pyrolysis temperature. So in this case, you're not performing over pyrolysis or under pyrolysis in your sample. So that's where EGA comes in. Very, very important first step for you to understand what's the optimal temperature is for your flash pyrolysis, for example. And then we perform flash pyrolysis, and the pyrogram obtained from the single shot or flash pyrolysis correspond to all 5 zones in the EGA. So all the additives and polymeric fragmentation comes in one pyrogram, as you can see here. What are the advantages of single shot? Well, obtaining the entire organic information of the sample in one pyrogram, which is pretty fast and simple analysis. Third mode of operation, a double shot. So what is a double shot analysis? Double shot is a process of performing two GC analyses on one sample. How does it work? First, the volatile fraction of the sample, such as any residual solvents that you might have, chemical additives, monomers, oligomers, they're all thermally desorbed, and then chromatography is separated and identified by MS. So no more solvent extraction. Think of it as a thermal extraction of your additives from your sample. And then second, after the completion of the GC analysis of the volatile fraction, the sample is again dropped into the furnace and pyrolyzed, providing the information of the polymer fraction. One important point I want to make here is the fact that the cup in a double shot move comes down first for the thermal desorption, goes back up again in an ambient temperature, so you're not really exposing your sample to any heat in between of your runs. Once the thermal desorption chromatogram is obtained, as you could see here in this example, the first chromatogram, and your furnace is ready for the second shot, which in this case was 550C, the cup free falls again into the furnace for doing the flash pyrolysis. So performing double shot on an eyeliner using our obtained EGA, we were able to identify the optimal temperatures and separate the additives and volatile compounds from the polymeric portion of the sample. What are the advantages? Obtaining separate sets of volatile and polymeric information in the same sample, which could really simplify the data analysis of your sample. And then lastly, what is hard-cut EGA GCMS analysis? Each thermal zone is sampled or vented independently according to the EGA thermogram. How does it work? The analysis of each thermal zone yields a chromatogram containing only those compounds evolving from the sample of the selected temperature range. So for the eyeliner example, using the hard cutting mode of operation, we were able to obtain separate GCMS chromatogram for each zone of the EGA. So in this case, 5 zone A, B, C, D, and E. Zone A was performed from 40 to 120, then 120 to 220, all the way to zone E. So what are the advantages of performing hard cutting? Obtaining detailed characterization of a sample, simplifying your data set, really yields simpler, higher quality chromatographic data, and also reducing your data processing time. So with all that, this is the end of part 1, and now I would like to turn the mic to Professor Advincula.
Well, thank you very much, Rogine, and I'd like to thank the audience for your participation in this webinar, and I hope at the end of this webinar you'll find it useful even to ask a lot of questions. And I would like to introduce myself. I'm a professor at University of Tennessee and also with Case Western Reserve University. I recently moved to University of Tennessee as a governor's chair. You may reach me at my email as shown in the slide at your convenience, even after the webinar if you have further questions. So today I'm going to talk, perhaps demystify some of the interesting uses of GC MS pyrolysis in reverse engineering. And I'll show this by examples via 3D printing and coatings projects. So our group is largely a materials, nanomaterials, nanostructuring group. We deal a lot with interfacial chemistry, nanostructuring of nanomaterials such as graphene, carbon nanotube. I have worked a lot with industries in various projects related to coatings, 3D printing. As well. And I am the editor-in-chief of MRS Communications, and I'm representing here by way of Case Western Reserve University, work that we have done related to GCMS pyrolysis. And lastly, I'd like to thank my research group as shown in this nice picture last summer, and I still have four PhD students who are completing their degree at Case Western Reserve University. So back in 2016, I was invited to give a talk at the World Economic Forum to describe the future of 3D printing. And there I describe the possibilities in uh, tissue engineering, robotics, space manufacturing. But what's important is 3D printing is with us today, in that various types of formulations, filaments, plastics are used in techniques like FDM, SLA, SLS. These are um, different techniques that are popular and well used not only for rapid prototyping but production. So the good news is one can access 3D printing today, and you can buy one of your own from Amazon.com, for example. Now, compared to other types of manufacturing and uses of plastic, 3D printing shines where you have increasing complexity and high performance. In other words, it doesn't compete well with things like injection molding, extrusion, thermoforming, but it's very important to use new materials, improve materials, or even improve existing plastics into the 3D printing because of the demand for complexity and performance. So as you can see here, a number of these techniques I mentioned earlier, from FDM, SLA, SLS, starts with filaments, powders, resins, composites, and so on. So what it is there's a demand for a hierarchy of materials performance. And when we talk about plastics, we could be talking about polyolefins like polyethylene, polypropylene, which are commodity plastics, all the way to high performance polymers like PAEC, PEEK, ULTEM, and engineering polymers like Kynar, etc. So not all of these are easy to 3D print, yet industry demands that we utilize various types of materials and their performance. In fact, not only thermoplastics, but thermoset resins, thermoset elastomers, thermoplastic elastomers, or rubber are increasingly being used in 3D printing. And so there is a price cost performance ratio that one has to optimize and make available commercially. But as you can see in this collage, the 3D printing gamut runs in many industries, from aerospace to marine, electronics, medical, and so on. And since this is a GCMS pyrolysis talk, I'll refer to some of my YouTube videos on 3D printing with high performance polymers. And in fact, you can 3D print a Jeep. Yeah, this is a wheelless Jeep that was printed at Oak Ridge National Lab. You can guess which parts are printed and not. But the important thing here is to demonstrate that even traditional or old designs, such as a World War II Jeep, can be manufactured today if you have the design and the materials. On the other hand, we use highly nanostructured materials based on nanocomposites that includes carbon nanotube, graphene, metal, nanoparticles, and so on. And here's just a sampling of the list of materials, techniques, and nanocomposite projects that we have. The bottom line is the materials used for 3D printing is quite varied. The commercial space is very wide and very much open. And there is a need to demystify a 3D printing material, or somehow in R&D or competitive development, one has to relate composition property performance that can be done by reverse engineering. So what is reverse engineering? Well, we can start first by understanding forward engineering. Forward engineering is, of course, development or R&D, where you want to have a product conceptualized, designed, eventually manufactured, implemented, and then commercially available. On the other hand, a reverse engineering is the reverse of the process, where you have a product and you want to go to the basics of what it was made of, how it was manufactured, its a structure composition property relationship, and therefore you're able to compare functionality. And for various purposes, use this to your advantage. For example, just simply trying to find out what a paint composition is made of, whether it's for forensic or competitive development. One can start by knowing that a paint is composed of many ingredients, from pigments to resins, and therefore one can apply a number of analytical techniques separating the solids and the liquids, and then using the appropriate spectroscopic, microscopic method, or even scattering X-ray methods to deconstruct the formulation or the ingredients. So there are various reasons for reverse engineering polymers and formulations. So it's not just copying the competitor's product or trying to do some espionage in terms of product development, but really you have reasons like poor documentation and therefore trying to have the components from an old formulation, or trying to prove or disprove marketing claims, or trying to assess competition's products performance, benchmarking, or if you're involved in litigation, patent infringement, failure analysis of your own product, or defect analysis, quality control, and so on. So this is just to tell you that reverse engineering is not a bad term. It is a very important exercise that is widely used in industry, but not too openly. So how do we start? Well, in this general scheme for analysis of formulation, whether you're dealing with paint, plastic, adhesive ink, etc., one can assess based on literature or product literature what are the possible ingredients. And this is not a secret. Some of them are labels, some of them are based on literature, things that are found in patents, etc. But a preliminary examination usually is based on optical, microscopy, visual examination, even some thermomechanical characterization is warranted. What happens is, if you're interested in the chemical composition or formulation, then you have to employ sometimes a very tedious separation of individual components from solvent extraction, centrifugation, filtration. Therefore, you will be able to separate solids versus volatile, which is not easy, versus soluble or solvent selective soluble components. And then you can employ techniques like infrared spectroscopy, NMR, GPC, XPS, X-ray, etc., to compare components found as resins, solvents, pigments, or additives. So just by looking at this chart, you know it's a lot of work. And the separation is not a guarantee that one can isolate pure components and even assign specific composition or purity. Now, in plastic deformulation, this is very specific. One can deal with a solid sample. Usually, thermal analysis is one of the easiest ones to use in terms of DSC, TGA, and DMA that allows us to look at the degradation temperature, the presence of a melting point or a glass transition temperature. Now, if you have a sample that you can pulverize and therefore separate perhaps soluble fractions, you can use solvent extraction, such as a very effective salt slat extraction, centrifugation, dispersion, and then filtration. The solid can be separated from the liquid and separately analyzed by X-ray, elemental analysis, or in the case of soluble components as well, you can use NMR, IR, and other spectroscopic methods. Now, if you have a surface before destructive separation, one can employ XPS, ATR, SEM microscopy, and looking at the bulk analysis, one can employ X-ray scattering diffraction methods. Now, this is not hard to demystify if you know your plastic chemistry. The resin or the polymer is basically the major component. So if we're talking about polyesters, polyurethane, that will be the major component. However, in processing, many additives are included, which would be your dye, your flow agents, mold release agent. That is the harder part, which is demystifying or deconstructing the remaining 5 to 1% of your plastic component. And that is why GC mass spec pyrolysis, as Regine has ably and very well reviewed at the beginning, is quite a game changer. With GC mass spec pyrolysis, especially with the method that has been perfected by Frontier Labs and in collaboration with Quantum Analytics. And by the way, I'd like to thank uh, Regine and Lauren and in general Frontier and Quantum Analytics for their support and their technical prowess in this techniques. One can utilize or even overcome some of these sample preparation procedures and employ very well and complement techniques like IR, TGA, NMR in a rapid manner. So as introduced earlier, there are several techniques, and here is just outlining the components. The main thing is that your pyrolyzer, as highlighted here, is really what allows you to do the sample analysis rapidly without much sample preparation. And the variation of techniques from hard cut to single shot, double shot allows you to focus on specific components or regions of your composition or thermal degradation. And so, again, without repeating some of those, this technique can be useful for reverse engineering, validation, failure analysis, and some of the techniques we have been developing in our lab. We have been using this actually for characterizing cross-linking density as well as molecular weight determination in conjunction with other techniques. So you've heard techniques like thermal desorption, evolved gas analysis, hard cut, etc. And these are the abbreviations that are shown in this method map. And the more you use them, the more you find, of course, the specific advantages of each one. The nice thing with this GC mass spec pyrolysis method is that it encompasses the three phases of your sample from gas to liquid to solid. Whereas if you simply use LC or LCMS or GC, GCMS, you're dealing only with specific phases or mobile phases during the analysis. The other thing is your inability, for example, to uh, focus on specific regions of the temperature, let's say with some of the more common pyrolyzer, means that you only have a one-way type of analysis from low to high temperature. Whereas with this uh, Frontier Lab Pyrolysis GCMS, you can jump right away to your temperature region of choice. And as you can see this here, the Pyrolysis GC mass spec encompasses, again, all the phases of your sample from gas, liquid to solid. And again, without reviewing much, EGA gives us the thermal map of degradation. It's very similar to thermogravimetric analysis, single shot flash pyrolysis. Based on the known temperature or degradation of the material, we can have a big distribution, or rather spectra, of the whole composition that includes the additive and the polymer. On the other hand, we can isolate the additive and the polymer by doing a double shot experiment. And with the hard cut, as I mentioned earlier, you can focus on specific regions and divide it into zones like A, B, C, D, and E. Okay, so I'll go a little faster here, and hopefully we can reserve more time for questions. Okay, and here the F search engine, which is a very important feature, allows you to rapidly identify fractions without being an expert in mass spec. In that this NIST originated library has been populated with many samples that allows you to do both quantitative and qualitative analysis with a simple or high confidential match of your spectrogram. Okay, so in other words, an anode material has a lot of chances in being determined even by GC mass spec pyrolysis alone. And of course, you can add FTIR, NMR, other thermomechanical analysis to complement your GC mass spec pyrolysis. And in fact, a very careful and complete work is as good for forensics or reverse engineering for rapid development of a new product or a competitor's product. So let me just use the rest of my time with this example. So polyether ether ketone is a very important high performance polymer that we have 3D printed, and we have recently reported its properties based on various printing methods and compositions. And here you can see that we have printed this polyether ether ketone samples with 3 different printers utilizing a commercially available polyether ether ketone filament. And they have various types of crystallinity as shown here. The bottom line is we published this work, and without GC mass spec pyrolysis, we would not have been confident in reporting their properties. And what GC mass spec pyrolysis did is it confirmed quickly, based on EGA, that we have a very high purity polyether ether ketone. Not much additives or none are present. This was processed at a high temperature as a filament, and the typical signatures for the structures associated with peak were observed in the mass spec. So very quickly, EGA and pyrolysis allowed us to confirm and confidently report on a commercial sample in a publication. Now, talking about rubber, we have been 3D printing different types of rubbers from NBR to polyurethane to natural rubber. And as you can see, there are many types of rubbers used in industry. Not much has been 3D printed, but they are very important industrially and manufactured using molding, extrusion, and other techniques. So just taking the case of thermoplastic polyurethane, so TPU here, typical case of a polyol and a polyisocyanate will have different types of MDI, TDI, or ability to segregate hard and soft segments. So this is a thermoplastic elastomer, very useful in many applications from automotive to biomedical applications as shown here. We have analyzed, and I'll show you why we did this a priori, because this TPU again was commercially available, and we were curious, if not cautious, what ingredients were used before 3D printing them and mixing them with graphene. So from the EGA thermogram, we confirmed that the typical composition can be divided into 4 zones, zone A, B, C, and D. And each zone can be focused on the particular composition. And from the flash pyrolysis up to 600 degrees C, what we confirm is that we have a distribution of phthalates, isocyanates, and polyols for the whole composition. But zone A, in particular, confirmed the presence of a dibutyl phthalate, a plasticizer that we did not expect. And during hard cut at zone B, we confirmed the presence of this aromatic diisocyanate. And the zone C and zone D mass spec again confirmed the presence of various polyol compositions, which will enable us to confirm whether these were based on bio-based polyurethanes or other types of commercially available polyols. The bottom line is this type of confirmation, which we could have done with longer methods of deconstruction involving separation, solvent filtration, application of NMR, IR, etc., would have been tedious, and if not for GC mass spec pyrolysis, we would not have been able to use this material for our research. So the interesting thing is we then took this TPU, we added graphene oxide, we were able to demonstrate that it has good blending properties. We 3D printed them, and based on the amount of graphene oxide, we can confirm that we have various types of thermomechanical properties as shown in this PowerPoint presentation. where the directionality as well as the presence or the amount of graphene oxide gave us a range of thermomechanical properties. So the bottom line is for nanomaterials and the TPU we used confidently, the addition of as little as 0.5 weight% graphene oxide gave us the best tensile modulus compared to a virgin sample without the graphene oxide. And this is one among the different type of studies that we typically do with nanocomposites. And they are also viable in terms of their um, uh, biocompatibility. Now, let me skip some of these examples in order to gain more time for coatings. We 3D printed paste based on what we call ketchup printing or viscous solution paste printing, as shown here. In fact, what this is a CNC movement of an extrudable paste that can be 3D printed, which allows us to 3D print, for example, cement or chocolate or thermoplastic elastomers, okay? And in fact, it enabled us to 3D print silicone. So let me skip these slides here in the interest of time. So in this case, the silicone elastomer we use, again, was a commercially available silicone from Home Depot. And silicone is a thermoset elastomer based on the cross-linking of the siloxane units in various forms without going into silicone chemistry. We then 3D printed them using a CNC movement. And again, by reverse engineering with Pyrolysis GC, we confirmed that the majority composition of this material is really a polydimethyl siloxane with the corresponding peaks of the cyclic oligomeric fractions that was confirmed by the spectral library. I will not go into other degradation mechanisms, but we describe this actually in a paper that is to be published soon. So we successfully 3D printed this with various size of the tips and resolution. And the bottom line is we confidently 3D printed the silicone using this mode. And we can get this shape or this particular silicone tennis ball. All right. So with the remaining time, let me focus on why paint and resin component analysis has a very important role when it comes to GC mass spec pyrolysis. So from architectural paint, industrial coatings, specialty coatings, with various paint compositions ranging from solids to resins to various additives that can prevent foaming, thickening, resins, coalescing, biocide agents. There's a lot of interest on demystifying, let's say, paint compositions from your competitor or from different types of product failures or looking at various blends or even just quantifying your source for raw materials. And we have major classes that we can divide from epoxies, polyurethanes to polyesters, silicones, as mentioned earlier. And a traditional method for structure composition analysis is again based on spectroscopy, mass spectrometry, of course, and other types of thermal properties or solution characterization, including molecular weight determination by GPC. So in a paint deformulation, you would start, let's say, with a liquid resin specimen. You can try to separate solids by centrifugation. You can try distillation to remove solids and distillates. From the centrifugation, you are able to separate fragments or fractions based on the pigments, the solvents, and the additives. Once you separate them, then you can apply the appropriate spectroscopic and even microscopic methods. Again, what this shows you is to do this job, you will do a lot of solvent extraction or sample preparation, and that can be discouraging. However, with GC mass spec pyrolysis, as I'll show you in some of these examples, this is done by simply scooping the sample from the source. And I tried to hide some of these product labels as best as I could, and I'll show you some examples. So for example, with an epoxy part A and B, epoxy and hardener. These are commercial samples and a fast drying polyurethane. You can see that the application of EGA, evolved gas analysis, allowed us to look at the composition of epoxy at a range of temperature. What this tells us is that we don't have low volatile components on epoxy. The library spectra confirmed the major presence of bisphenol A. So this is a typical epoxy resin, bisphenol A, and actually without further going into the double shot and single shot, we did classify the presence actually of some esters or polyesters in this component, which was found in the higher temperature range here. But here you can see, based on the pyrolysis of the epoxy resin, you can see the major components that we would attribute to the bisphenol A composition. And then the hardener is a typical amine composition. This isophorine diamine was confirmed by the mass spec library. And then these two peaks confirmed the presence of two fractions. And we were able to confirm that again by a cut experiment. But again, just to confirm, even from double shot, we can see that it's a mixture of two different types of amine diamine compositions. And again, some of the experiments to confirm the presence of other components on your resin hardener. So with the fast drying polyurethane, we confirmed several peaks here. We tried to see if there were plasticizers present or biocides. But what we found is this is a typical polyurethane composition. First, the hard cut confirmed the presence of these long chain polyol units. So this could be bio-derived. And then the presence of urea was a surprise to us, and that can be present in some polyurethane compositions. But more importantly, we confirmed the presence of this diisocyanate composition on the material by hard cutting. And this means that this fast drying polyurethane was aided by the action of these various components. Here, we confirmed that this is actually a bio-based material based on a oleic acid. And it's very well known that polyurethanes can be derived from bio-based polyols, for example. And here, the presence of various linoleic, lignocellulosic acids based on these components. Okay. So the bottom line is the demystification of this polyurethane was almost quite complete, even by GC mass spec pyrolysis alone. However, to improve the process and the identification, let's say for complete reverse engineering and perhaps forensics, we will need to purify some more and apply, let's say, NMR to confirm the presence of these different fatty acids. So without getting into more details, this is probably my last example before I take the question. So let's say this gloss protective enamel, which, as the label says, has various compositions declared on the hazard these chemicals list. By EGA thermogram, we were able to divide it into two zones, zone A and B. By the pyrogram, we can see different compositions from the oleic acids to the phthalic anhydrides and benzoic acid. This enamel composition could be various types of resins or alkyd resins that we typically use in the manufacture or formulation of enamel paint. And the presence of the long alkyl chain compositions was confirmed by this mass spec as well. So again, I'd like to leave more time for questions, and I'd like to finish here by saying that in GC mass spec pyrolysis, we have the ability to rapidly reverse engineer, quote unquote, a competitor sample, a supplier, a commercial sample that we can use for R&D research or publications use. And we are able to apply various experiments to mimic what could be done in a complete analysis that otherwise would have taken a lot of time with the application of NMR, IR, thermal analysis, and so on. So with that, I'd like to thank you, and I will be happy to answer questions from the audience.
Oh, great. Great. Thank you so much, Rogine and Dr. Advincula, for a great presentation. Yeah, let's get into some questions. The first question is, could possible chemical interactions between ingredients be determined?
So I'll try to answer that question, Regine. So when we say chemical interaction, I believe, or I am guessing the question says that what are the starting materials that reacted to form the product, or if there are chemical reactions that are ancillary to the product in case of degradation or oxidation. It helps if you have a suspect chemistry that might have happened or is happening prior to the product formation. So, for example, you know that a polyester would undergo esterification or hydrolysis. And you can ask the question, is that polyester made up of this type of acid or alcohol, or is it made up of polyethylene terephthalate ingredients, terephthalic acid, and ethylene glycol, for example. So it helps to know the chemistry. Once you have that, then you can use GC mass spec pyrolysis to deconstruct some possible compositions or create a method map by which you can do the reverse engineering. But again, the first thing you would do is try to guess the product chemistry and what it takes to either degrade or synthesize that a polymer or that organic molecule.
Also, Kristen, I would like to add that, as Dr. Advincula mentioned, in most cases, if you actually start with your EGA, follow the method map, because that EGA will give you a good understanding of the thermal behavior of your sample. So that allows you to not really perform over pyrolysis, which is like heating the sample more than you should, or underheat your sample that is not your optimal temperature. So finding that right temperature also helps.
Okay, great. Thank you. This next question says, I am trying to determine if one GC-MS footprint could serve both non-pyrolysis and pyrolysis sample prep. Is it possible to have one GC-MS footprint for both sample types, or is it preferred to have a GCM with pyrolysis sample prep and a second GC-MS for organic solvents?
Well, if I'm understanding
Regine,
the
would you
question
like to take
correctly, sure, Dr. Advincula. If I'm understanding, Christian, the question in a clear way, well, actually, when you have the pyrolyzer on your system, you could still do your GCMS analysis. The pyrolyzer can be used whenever you want to do organic chemical composition, because you have a temperature that goes more than 1000 C. So if you want to go after those polymers, you could actually break it down and perform pyrolysis GCMS. But meanwhile, you could also perform your own GCMS on your system, not using the pyrolyzer, if I'm understanding the question correctly.
Okay. Next question, is there a separation of solid components on a paint formulation needed prior to GC-MS pyrolysis?
Okay, so I can answer that question, and we have done this many times. The answer is typically no. You can get the solid paint sample, scrape it directly from a car or a product or a chip from an unknown, and introduce it on the sample holder of the pyrolyzer. And the method that you can choose, let's say if you start with evolved gas analysis, allows you to have a map of the degradation components of that paint sample. Now, once you have the pyrogram, you can have a view whether that paint sample has pigments, polymer resin, which is the majority component, If you're interested in other solid additives that might have come, usually they degrade at a higher temperature. And then you can focus on specific peaks or regions using hard cut. One thing that can be used with a double shot technique is it allows you to get the additives and the polymer components at the same time. So mind you, most additives, if they are small molecules, will have a lower degradation temperature, whereas polymer resins or latex particles would have a higher temperature degradation. So that gives you a certain picture of where the region is important when you're focusing in both. Now, if you have a volatile component that you're interested with, let's say in an actual paint, which has some volatile component, you can actually use a cryogenic technique or basically start your EGA or experiment with a lower temperature. And that option is also available with the Frontier Lab combination with quantum instruments such as the Agilent GC mass specs.
Okay, the next question is, how do you determine cross-linking? Can the extent of cross-linking be determined?
Okay, I like that question, and that's probably a holy grail in some of the thermoset elastomer components. So traditionally, one way to do it is to, of course, know the chemistry and to make model studies. That is, you either induce very high cross-linking or low cross-linking, and then follow the peak. Now, what we have been doing in our lab is we're actually doing some labeling which involves trying to separate the mass spec attributable to the cross-link or branching units itself from the linear components. And one thing that we do sometimes is we try to either use a longer alkyl chain or we try to include a phenyl or unit or even a fluorinated unit. But that, of course, can change some of the cross-linking chemistry. But what we have done is we will do what I call calibration studies, where we vary the degree of branching on various or cross-linking on various compositions. And because we can do an internal calibration by GC mass spec or follow the development of peaks and various composition with this technique, GC mass spec pyrolysis, we're somewhat able to quantify the degree of branching. Again, the advantage is we don't have to prepare tedious sample preparation, separation by solvent extraction. We simply put the thermoset sample directly on the pyrolyzer, and that saves us a lot of time. So that is the gist of our methods for cross-linking determination in samples.
Okay, the next question. I found it is difficult to identify low percent components by pyrolysis. How low percentage can you reach?
I guess I can comment on
Regine,
a
maybe you
little
can.
bit. Yeah, maybe I can comment on that. So it really, I want to mention that first of all, it's really dependent on the system configuration that you are currently using. Also depending on a mixture of your sample and what components you're trying to go after. Typically, if you want to have more selectivity and sensitivity for really trace amount, BP's amount, maybe that will be something to use MSMS. But we've seen customer using ppm type of a level work with a single quad MS, but again, depending on the mixture of the sample and how your system configuration is currently in terms of your MS sensitivity.
Mm-hmm.
Okay.
And I can confirm that, Regine. So, for example, with that, very low compositions, it will now become dependent on how sensitive your mass spec instrument is. And the other that one can do is, of course, do some purification. If your suspect minor component is very small, you might have to do some sample purification then in order to enhance the amount of that small component.
Okay, the next question. Can GCMS be used to determine monomers distribution in polymers?
Very good question. Yes, in principle, especially if your monomers have very separated peaks. In other words, between acrylate, vinyl, and other types of acrylate, methacrylate monomers, it's very hard. But if you are comparing, let's say, acrylate versus styrenic or acrylate versus fluorinated samples, or one which contains long alkyl chains, it's easy. So again, the further you can separate them, the better. And then once you know or have done your separation studies, you can do some sort of calibration in order to quantify them. Now, of course, some easier methods perhaps could be complementing it with NMR and IR. But again, GC mass spec pyrolysis is just one tool you have in your war chest. And you can combine a number of analytical techniques to give you a complete picture of your distribution.
Also, Kristen, I like to add to Dr. Advincula's comment regarding these monomers. Of course, depending on what monomer you're trying to go after, what is the polymer of the mixture, but most of the time, choosing the right mode of operation will also help you really in identifying your monomers versus from the breakdown of your polymer. For example, if you have a polyestyrene and you're trying to quantify your styrene monomer, if you only perform flash pyrolysis, you can really tell if that peak that is corresponding to styrene monomer, is it from your, say, on-reactive raw monomer, or is it a breakdown of your polymer? But once you perform a double shot analysis or something that you can thermally extract your monomer from your mixture, then you can separate those, as Dr. Advincula mentioned, and kind of analyze your monomer from the polymeric portion of your sample.
Okay, next question. How can you determine structure of polymeric modifier in inorganic pigments? Which method can we use? EVA-MS or TGA-MS?
EGAMS allows us to look at more or less the composition similar to how we would use TGAMS. The advantage is that this is connected, uh, of course, to a specific mass spectra, but also it allows you to, with the GCMS pyrolysis anyway, with this technique, it allows you to go to specific peaks using the hard cutting instrument. Now, with regards to uh, polymer components. Again, if you have an idea of the melting point, the degradation temperature of the polymer or the polymer blends, you can guess which regions they should occur in the, let's say, uh, pyrogram and your thermogram as well. So it depends. The rational thing is you have to do some homework at the beginning in order to make the most of your uh, GCMS pyrolysis experiment.
Okay, we have time for one more question. Is there any value of using GC-FTIR with EGA stream?
Regine, can I give that to you, or I can follow that
Sure,
after?
sure. I mean, of course, every instrumentation has its own advantages. I can't think off the top of my head have an example of a pyrolysis with the FID or FID with MS, but really with pyrolysis GCMS, as Dr. Advincula mentioned, that's a complementary technique to FTIR. Whereas with PyGCMS, a lot of those sample preparations are eliminated, and you get a lot more detailed information on organic composition analysis of your sample. Of course, with FTIR, you could still get the functionality groups. In some cases are harder because you have to perform a lot more extensive sample preparation, and sometimes the mixture of the sample that could hide some of especially the additives inside the sample. But overall, they're complementary techniques.
Okay, great.
And
Thank
I
you.
agree. And
Go ahead.
both are useful, yeah.
Okay. All right. Well, that's all the time we have for questions today. If you submitted a question that we did not get to, someone will be getting in touch with you after the webinar with an answer. Please join me in thanking Rogine Belganay and Dr. Rigoberto Edvincula for their presentations, as well as a big thank you to our sponsor, Quantum Analytics. If you have any additional questions or comments, please don't hesitate to click the Email Us button on the console. As you exit today's webinar, please take a couple of minutes to complete our survey. We strongly welcome your detailed comments. And please visit webinars.pcimag.com for the archive of this presentation, as well as information about our upcoming events. We appreciate your time and hope you have found this webinar to be a valuable experience. Thanks again for joining us.